This is another problem about blood, and it says the amount of heat per second conducted from the blood capillaries beneath the skin to the surface is 240 joules per second. The energy is transferred a distance of 2.0 times 10 to the negative 3 meters, so that's 2 millimeters, through a body whose surface area is 1.6 square meters. Assuming that the thermal conductivity is that of body fat, determine the temperature difference between the capillaries and the surface of the skin. So let's see what is given. First of all, they tell us what the heat is conducted per second, so I'm going to write this as Q divided by T. So that one is given. Then the energy is transferred a distance of 2.0 times 10 to the negative 3 meters. So D is given, a distance. And then the area of the skin is given, 1.6 square meters. That's a lot of skin. That's about 17 square feet. Assuming that the thermal conductivity is that of body fat, so that would be implied or given. Have to be looked up in the book. So that's the K is given. Determine the temperature difference, delta T, and then there's the question mark. And then, of course, the only equation that applies to that would be the equation for the conduction of heat, which is given then as Q equals, and then Ka delta T times time divided by L. For some reason they always use L for length. I guess they're looking here at rods of a certain length L, but for most cases it's a thickness, and I guess, of course, the distance D here is the same as L over here, and we're supposed to figure out what the temperature difference is. So when I do the algebra on this one here, it's going to be Q over T. Actually, I'm going to redo that because that Q over T is already given, so I'm going to write it separately. This one here is one number given as 240 joules per second, and then times the L or the D, and then divide that by K and A, the A being, so this, the D being the 0.002 meters, the K being given in a table in the book, let's see, other materials, as 0.20 joules per second meters and Celsius degrees, and the A given in the book as 1.6 square meters. Equals, and then of course you're going to come up with Celsius degrees for the answer, and it's going to be in the neighborhood of like 1 to 2 Celsius degrees, and so that's how much warmer the blood is just beneath the skin surface. In fact, this is what I found, just a quick look up. Blood temperature is 41 degrees Celsius, 108 Fahrenheit, always slightly higher than body temperature. Actually, this is higher by about 10 degrees here in the book. Let's see, blood beneath the skin. So these are just beneath the skin, so these capillaries might be different from the average blood temperature, and might be cooler, yet a little bit higher, so around 100 Fahrenheit for the capillaries as mentioned in the problem. This problem is about the skier, and it says, a skier wears a jacket filled with goose down that is 15 millimeters thick. Another skier wears a wool sweater that is 5.0 millimeters thick. Both have the same surface area. Assuming that the temperature difference between the inner and outer surfaces of each garment is the same, calculate the ratio wool to goose down of the heat lost due to conduction during the same time interval. So I'm going to see what is given and what they're asking for. What's given is the thickness D or L, and that is given for both of them, for the wool and for the goose down, and the heat conductivities for either one we just look up in the table. The area actually is not given, so we'll see what happens there. The time, it says the same time interval for both of them and the same area for both of them, so we'll see what happens there. And then what we're supposed to figure out is the ratio of the heat loss to the conductivity. So the heat ratio of the wool versus goose down. So I'm going to write here W and then G for goose, and that's what we're supposed to figure out. Okay, of course, heat conductivity, so I'm just going to write this down. Q equals K A delta T time divided by L, and then I'm going to copy this one here because the first one is for wool and the second one is for the goose down. And then I'm going to write that Q of the wool divided by Q of the goose down is all of this here divided by all of that. Notice that with the same area, that divides out with the same temperature difference. That's what they say, and I forgot to write this down here. So delta T. There we go. So none of these is given, but they're saying that the A, the delta T, and the T are the same for either one of them. So when we determine the ratio between the two, they all divide out. And then what happens is that we have a ratio of the heat conductivities and the thicknesses because they were different from one to the other. So here I would have K over L for the wool times L over K for the goose, and of course that's the reciprocal because we're dividing by the goose down numbers, and then equals, and then as shown here all of these are given and we come up with a ratio with no units. And I'm not going to calculate it because you can easily calculate it, but when I look at the numbers in the book, then the conductivity for wool is a little bit higher than that for goose down, so it's a little bit worse in insulator than the goose down. So as I said, that's a little bit higher, and then the wool has a thickness that is less than that of the goose down. So taking those two numbers into account, what will happen here is that the ratio here is going to be a number larger than 1, in the neighborhood of like between 5 and 10, I guess, somewhere around there. Maybe a little bit less than 5. And that means that through the wool sweater, the heat is conducting more easily, more heat conducts out. And as I said, that makes sense because its conductivity is a little bit higher, so its insulation is worse, and it's thinner than the goose down in this problem.